looking at the Euler totient function. Oops, right, I need to print it. Okay, so we've introduced this relationship of congruence modulo n, and we found that when we formed this reduced system of congruence classes modulo n, we had a set which formed a group under the operation of multiplication of congruence classes. Okay, so this is the end of chapter 4. Last couple, page 30, last couple pages of chapter 4. So you only include the congruence classes of integers which are coprime to n, coprime to the modulus. They are coprime to the modulus, i.e. they have a greatest common divisor between a and n is equal to 1. Then we include that congruence class. That will have a multiplicative inverse, okay, an inverse with respect to the operation of multiplication of congruence classes, and this thing will form a group. Okay. So it's the Zn. Zn without the multiplication superscript. Zn refers to the set of all the congruence classes, so the partition of the whole integers. Zn with the superscript multiplication sign means just those which are coprime to the modulus, and that forms a group. So we introduced the Euler totient function, which is the size of this group. It's traditionally denoted by the letter phi, phi of n. So phi of n is the size of this multiplicative group, i.e. it's the number of integers less than n which are coprime to n. Okay. But because it gives the size of this group, it's quite important. And we would like very much to understand this function, phi, and get a nice way to evaluate it. Now, we can evaluate it straight away from the definition. So if I ask you what phi of 100 is, well, you can, without knowing anything else, you can just operate the definition. You can check each of the numbers 1 up to 99 and pick out the ones that are coprime to 100 and just count them. And that will give you the value of phi of 100. Okay. Well, 100, except you already know the greatest common divisor of 100 with itself. 100 and 100 is 100, so that's never going to be coprime. You know, a number is never going to be coprime to itself except for 1. So you already can evaluate the function. However, that, you know, in a way that's quite a naive way. You know, all we're doing is just working with the definition. We're not exploiting any more knowledge about the structure or behavior of this function. So we'd like to approach this question in a more sophisticated way. It can be helpful just to look graphically at what the function is doing. So here in Sage, so this command here at the top, L. So this gives me a list of Euler phi values. So Euler phi of n for every n in the range 1 to 5,000. So L there is a list 5,000 elements, and these are the values of the Euler phi function. So you can see the values are increasing because when you look at a larger number, the more the more numbers less than it there are, and so the more numbers there are less than it that are going to be coprime. Of course, it increases generally, but you know when you look at some later values, so you know 600 odd, 200 odd, 600 odd, 200 odd, 400 odd, 300 odd, 500. So there's no regularity to it. It's hopping up around between large-ish values and smallish values as you go through. It's not very easy to pick out anything just from staring at lists of numbers, so we should look at a plot of it. So this is the first, so that's a plot of the first 5,000 values. Sorry, scroll past it. The first 5,000 values of the Euler totient function. So we got n from 1 to 5,000 here, and each dot, each dot shows the value of the function on that integer n. So it's broadly increasing, but when you look at around any particular region of values, say look at all the n's near 4,000, you see quite a lot of variation, ranging from about a value of 4,000 all the way down to a value of about 1,000. Okay, so there's quite a lot of variation. There's quite a large range, and as suggested there, that range is increasing. It's kind of fanning out. So there's, what kind of, we certainly wouldn't expect any kind of very simple formula for what phi of n is in terms of n. It's certainly not any kind of polynomial in the value n. Now I left you with we ended with a question last time about what was phi of a prime. So how many numbers less than a prime are co-prime to that prime? Well, all of the numbers less than a prime have to be co-prime to the prime, because a prime doesn't have any factors to share with any of the numbers less than it. So phi of p is equal to p minus 1 for every prime p. We ended with that last time, okay? So it's p minus 1, so it's just the numbers 1, 2, 3, all the way up to p minus 1. So those numbers are all located along this top edge here. So these are all the primes along the very top of the picture here. Okay, those are all the numbers which have maximum maximum feasible phi value. Okay. Highest the value of phi n can be based on n is 1 less than n. And that occurs when n is a prime number. Well, you can see they also get down fairly low, and like these values of n which have a relatively low phi value, those are numbers which must have a very rich factor structure. They have lots and lots of factors. So it's very hard, this n up here, which is quite a large n, around 4,700 somewhere, but it has a very low phi value. So it's very hard for a number less than this number to be co-prime to it. It must be that this number has a very rich factor structure. So we can kind of glean things from looking at the graph, and there's these lines of concentration. This top line here, there's a very strong accumulation line here through the middle of the planet, and these other strongish lines out here. So there's definitely a story to tell to explain, why is it that there's a lot of points clustering around that line? Why is it that there are a lot of points clustering around that top line as well? But there is a lot of describing to it. Okay. Any questions so far, or observations? Okay. So what we seek now is a better way to evaluate the function rather than just simply counting all the numbers that are co-prime to n in each specific instance of n. We want a better description of it. And well, maybe I should have done a more of a discovery type presentation of it. But here at the front of chapter 5 is this formula. So this is the main subject of chapter 5, which is establishing this formula. So this is called the product formula for the Euler phi function. Okay, it's a product formula. You can recognize it, so it's got the large pi sign. So it's a product of all these terms. You've got your index I ranging from 1 to r. Now, the things in the factors that you're multiplying together are these pi's and ai's. So what are they? Well, the pi's and ai's, that's the information in the prime factorization of n. Remember, we proved the fundamental theorem of arithmetic. Every integer n has a prime factorization. And this is the kind of common notation we used. We wrote n as a product of primes, pi, raised to the power ai. And for any particular n, these will run from I equals 1 up to r. So this n has r distinct prime factors, p1, p2, p3, and so on. And they each occur to a power ai in the prime factorization. Then the value of the Euler totient function is a very closely related product. Okay, you can see what's going on here. So we reduce the power of each of the pi's by 1. We've got pi to the power ai minus 1. And then there's a new factor introduced for each prime, which is pi minus 1. Okay. So now this is a nice formula that allows you to find the value for phi of n, given n, and given that you know the prime factorization of n. And in number theory, the prime factorization is a very good way to consider to consider integers in terms of their prime factorization. And so this is a very nice expression, and so you kind of consider this formula as giving you a good understanding of the Euler phi function as it behaves on an argument n based on the prime factorization. Okay, but how are we going to establish this? So it isn't just presented as one single proof. We kind of split up the work into a number of kind of smaller lemmas and so on, results leading to it. But what we give here at the beginning is a sketch of the proof. Okay, so this is a sketch of the argument, which makes a number of assumptions in it, but gives the overall shape of the argument. Points out a number of results we're assuming in giving this overall shape of the argument. And afterwards, we'll go ahead and prove each of those important steps, or those assumptions that we made about it. Okay. Firstly, we'll prove a special case, okay? Not where we're evaluating phi at a general integer n, but just at a very specialized integer, integers which are powers of a single prime. So integers which have the form p to the power a. One fixed prime p, I'm just considering the integers which are powers of that prime. Now, given this formula up here, this is what we expect the value of phi of p to the power a to be. Okay. It's just the case of this formula here where r is equal to 1. The product as I goes from 1 to 1, so really it's just one term. Prime to a minus 1 times p minus 1. So we'll establish that it's true for powers of primes. And then we'll make the leap and say, well, if it's true for powers of primes, therefore it must be true for every integer, because every integer comes packaged up as a product of powers of primes. That's what we see. That's how we think of n and prime factorization. Well, what we need to make the step from a power of a single prime to a product of a number of powers of primes, we need to know that the function phi is multiplicative. Now, what's this? This is a new term we're introducing. In number theory, we're going to say that a function is multiplicative if it acts like this. Now, this kind of, very much compare this in your minds with linear transformations. With Stephen in linear algebra, you're studying linear transformations. So a function between vector spaces is linear if phi of a sum is equal to the sum of the phi values, or even more than that, because you've got another operation, scalar multiplication. If phi of a linear combination is equal to the linear combination of the individual phi values. Well, this is very much the similar kind of structure, but in a different context. Here, we're imagining ourselves in this multiplicative structure of integers under multiplication. So a function is multiplicative if phi of a product a times b is equal to the product of the individual phi values, phi of a times phi of b. Now, not for any old a and b, only in the case where the two factors a and b are co-prime to one another. Okay? So we say a function is multiplicative if it factorizes like this: phi of ab is equal to phi of a times phi of b on co-prime factors a and b. Okay? So it's not as strong as saying that it factorizes like that on every product, only on those products that satisfy a certain condition, co-prime products. Okay? If we know that the function is multiplicative, and we also know it behaves like this on powers of primes, then that will establish the full formula for us. Now, I spell out the argument there, but I maybe present it a slightly different way on the pen and paper here. Just, oops, sorry. Just for variety. So we have to prove these things, but assuming for the moment that phi of a power of a prime is equal to what it's supposed to be. So phi of a power of a prime is equal to this, and if phi is multiplicative, these two will combine together to give us the general result. Okay. So then we can. So this is the rest of the argument. If we let n, if we consider an integer n by its prime factorization. So the prime factorization of n, or the canonical form of n, prime factorization of n. It's important to know, so n has r different prime factors, p1 up to pr, and each of them occurs to the power ai in the product for n. So then all we have to do is just make this observation. If I is not equal to j, then two of these prime factorizations, two of these powers of primes, pi to the ai and pj to the aj, these two integers will be co-prime. Okay? Because they don't share any factors, do they? Because what are the factors of pi to the ai? It's just the prime pi, or pi squared, or pi cubed, etc. What are the primes of pj? Just pj squared, pj cubed. So all the factors that this has, are completely different to the factors that number has. Okay. If I is not equal to j, then these two powers of different primes are co-prime. So in other words, their greatest common divisor is 1. So that implies basically that phi of n, which we now have as phi of this product, basically means we can interchange the product sign and the phi. Okay, because we're going to say phi of the product of all these numbers is going to be equal to the product of the individual phi values, because those numbers that we're factorizing it up based on are all co-prime. Okay. Now, to do this, what's given in the notes is this argument, but done in a more careful, rigorous way, and it's done in an induction type way. So first doing it for cases where r equals 2, then doing an inductive step, so then you know it for r equals 3, r equals 4. For integers n, which have any number of distinct factors. The justification for this step is since phi is multiplicative. But then what you're looking at is this product from I equals 1 up to r, a phi of a power of a prime. And so if we've also got that result, then we can write this as pi to the ai minus 1 times pi minus 1. Okay, so this will establish, so this here is the formula that we want to arrive at, that we want to prove. So let's just see an example. I asked you rhetorically before what phi of 100 was. So if you think of 100 as its prime factorization, so 100 is 4 times 25, so it's 2 squared times 5 squared. Okay, so that's the prime factorization of 100. So according to this formula, it says, well, you take 2, you reduce the power by 1, so it's now just 2, and you multiply it by 2 minus 1. Then you take the 5 squared, you reduce the power by 1, so it's now just 5 to the power 1, and you also multiply it by 5 minus 1. So it becomes 2 by 1 by 5 by 4, which is what? 14. So there are 14 numbers which are co-prime and 100. It's basically all the numbers between 1 and 100, except you have to exclude all of the even ones. So you got factors of 2 there you have to avoid. And you also have to avoid all the multiples of 5. You avoid all the even numbers, well, there's 50 of them, so you chuck 50 of the 100 away. And a few extra ones, all the multiples of 5, which are not multiples of 2. So that's 5, 10, 15, 20, 25, 30, 35, 40, 45. No, I went through 40 there. I miscounted a few. But there's 10 other numbers, which are multiples of 5, which you already thrown away, which were already explained by you. Okay. If I asked the computer to give me what's Euler phi of 100, it would tell me. So that's the proof of this formula, except we made 2 assumptions in it, which we haven't proved yet. Okay, so these 2 assumptions at the top. That the special case, when you evaluate it on a power of a single prime, be of it that it is multiplicative. So multiplicative means, when a function is multiplicative, it means that you can always evaluate it on an integer by using the prime factorization. You can always make this move that to evaluate the function on an argument, it's just the product using the prime factorization of the argument. It's the product of the function evaluated on each power of a prime that is in the prime factorization. It's generally useful property to have for a function in the context of it. So let's go for the first of these properties here, which is phi of p to the power a. Let's show that that has the required form. So this is lemma 5.2 in the notes. The proof is in the overall result. So lemma 5.2 is that phi of p to the a minus 1 times p minus 1. So we want to prove that. A be some integer, positive integer exponent. Now, here we're going to have to use our original definition of the function phi. So we will count the number of integers. Count the number of integers n, which are in the range between 1 and p to the a, that are coprime, or that satisfy GCD of a p to the a equals 1. So we want to count those numbers between 1 and p to the a that are coprime to p to the a. And we count them by counting the ones that aren't. So we'll pick out, we'll identify to p to the a. And then the ones that are left are the ones that are coprime. Okay? So identify those n such that GCD of n and p to the a is greater than 1. So what are those numbers? These n are exactly all those n divisible by p. You see, how can you have a greatest common divisor of n with p to the a which is bigger than 1? It means you have to share a non-trivial factor with p to the a. Now, what kind of non-trivial factors does p to the a have? Remember, p is a prime number. So the only possible factors of p to the a are p squared, p cubed, all the way up to itself, p to the a. So if, let's say we're looking at p to the power 5, the only factors that p to the power 5 has are, well, 1, which is the trivial factor, but p cubed, p to the power 4, and it's. So the only way to have a factor of p in you. So the m are all the multiples of p. So again, we keep rephrasing this question: how many multiples of p are there in the range 1 less than or equal to m less than or equal to p to the a? Well, with these we can literally just count. We do it carefully. The first multiple of p is p. You're starting to see the picture. 4 times p, 5 times p. All of these numbers will not be co-prime to p to the a, right? Because they all share at least a common divisor of p to the a. So we keep on knocking these numbers off. What's the last one that you arrive at? What's the last multiple of p that you encounter in this range? P to the a, because the endpoint is actually a multiple of p. Now, how would I write p to the a to fit into this? Sorry? No, this is p to the power a.
Yeah, but p to the power of a minus 1.
Yeah, because I'm writing each multiple of p with the one of the p's with the p factorized out. So my last one I want to write down is p to the a, but to fit it in with this sequence, it's p to the a minus 1 times t. You see that now? So how many numbers have I listed there? It's unclear because there's a dot, dot, dot in the middle, but how many numbers have I listed there? Just count them.
A minus 1 numbers.
No?
Before n.
Yeah, there's many that I haven't listed, but if you imagine the complete list, how many of them are in the complete list? Just count them. There's 1, 2. Yeah, that's the last. You start counting them. 1, 2, 3, 4, 5. P to the a minus 1 is the last one you see. So there's p to the a minus 1 numbers here. It's quite an appealing argument. You set out to do it, and you just count them. As long as you set it out carefully, there they all are. Now these are the numbers. These aren't the numbers that we want. These are the numbers that we don't want. These are the ones that are not co-prime to p to the power a. We want the ones that are co-prime, so the ones that are left behind. So how many numbers were we considering originally? We were considering all the numbers in this range. And there's p to the a of them. Okay. p of m satisfying 1 less than or equal to m less than or equal to p to the a that are coprime to p. The size of the domain was p to the a, and we just subtracted the number of ones which we didn't want, which is p to the a minus 1. Or another way to write that is p to the a minus 1 times b minus 1. As required. That's exactly what we're doing. So p to the a is p to the a minus 1 times p minus 1. So here we've identified it. Just using this nice, simple, direct counting method. Is there any questions about it? Is that okay? Yeah. Here. So it's p to the power a minus by p. So it's p to the a. Yeah. But I wrote it in that way to fit in with this pattern. 1 times p, 2 times p, 3 times p. Because remember, I'm counting the multiples of p. So I want to list all the multiples of p in a way that shows they are obviously multiples of p. So some integer times p. And just when I write them like that, you can literally just count them. Because there's 1, 2, 3, 4, 5, p to the a minus 1.
Yeah.
Sorry, what? So, just to be clear, because we made a few moves there, we wanted to establish this formula for the function phi. Now, the original definition was phi of n is the number of numbers less than n that are coprime to n. Yeah? Well, no, well, here we're talking about p to the a, but just in general, phi of n. So what this is, phi of p to the a is the number of numbers less than p to the a that are coprime to it. We arrived at that number by counting the ones that aren't coprime and seeing what was left behind. We got rid of all the ones that aren't coprime. How many numbers did we chuck away? We chucked away p to the a minus 1. And there was p to the a of them there to begin with. So the number left behind is the difference, p to the a minus p to the a minus 1, which factorizes into the required form. Okay. Okay. Now, as you can see in the notes, if you look at the bottom page of 35 and the first half of page 36, it takes almost a whole page to prove that the function is multiplicative. So that's where a lot of the argument is. Establishing it for phi and a prime power was just a relatively straightforward counting argument. To prove it in general, we're going to have to prove that it's multiplicative. Now, I think we'll tackle that. We'll go through and explain that proof next week. I'd encourage you to read it in the meantime. Again, it's I keep saying simple, I should say simple all the time. It's another counting argument. It's based on counting numbers in this grid up here. So it's kind of a visual type argument as well, or at least aided by a picture, by that grid of numbers there. But we'll talk through that next week. Because the main point we're driving home, the main So what this is all about is working with this formula here. I'm working with the definition of the Euler phi function in terms of this formula. Okay? So next week we'll look at explaining why the function phi is multiplicative, although I encourage you to read it in the meantime, and we'll talk through the proof next week. And yeah, we might start doing a few of the relevant exercises now with half of you when I see you now in the tutorial, the other half on Friday. And in my second lecture next week, we'll look at some of the exercises as well. Okay? So stop there for now.